Now we will see the capacitor. What is the capacitor? For a capacitor, time domain representation is I of t is equal to C times d divided by v dt times v of t. So this is nothing but the input voltage v of t. We are deriving the input voltage with respect to time and multiplying with the capacitance value. Similarly here. So here also the same. So this is the current due to this applied voltage. We are derivating and then multiplying with respect to the inductance value. So now if we take the Laplace transform of this equation, then what will happen? L of I of t is equal to L of C times so V dash of t. So the dV of t divided by dt, I simply call this as a V dash of t. So 1 times the derivative. In case if I have the d square, then I have to put V double dash. So this is a simple derivative equation. So I write like this. So now if I make the Laplace transform, then what will happen? This I of t will become capital I of s is equal to this equation, right? So C times S times V of s minus V of V0, that is the initial voltage across the capacitor. So if we simplify, then it will be S C times V of s minus C times VO or V0. So V0 is always representing the initial voltage. So if you just simplify it furthermore, it will be like this. V of s is equal to 1 divided by S times C. C is the capacitance value. S is the Laplace transform variable, the complex variable or complex number. And I of s, that is the current flowing through this capacitor, plus V of 0 minus divided by S. This is the initial voltage across the capacitor. Before I close the switch, what is the voltage across this capacitor? So note that the initial conditions can be represented either as a voltage or current. We will see equivalent circuit. So this is the equivalent circuit, same like what we had seen in the capacitor, in the inductor. So we have the capacitor, and across the capacitor we are applying the voltage V of t. Because of this applied voltage, the current is flowing through I of t across this capacitor. So because of this current flow, we have the voltage drop or voltage storing in this capacitor. That is, and before this current flows, is there any voltage already existing in this capacitor? That is represented by V of 0. And the polarity you can see here, the same polarity as the supply voltage, but plus and minus. But in the inductor, plus will be here, minus will be here, opposite polarity. So now if we make this is the equivalent circuit of the capacitor in the time domain. Now if you make the equivalent circuit in the S domain, what will happen? Same circuit, we are putting this one. The initial voltage we are putting like this, plus and minus, same polarity, and then like this. And the supply voltage, capital V of S. Because of that, the current is capital I of S, and C is represented by 1 divided by S times C. C is the capacitance value. And we are representing the initial voltage in series, plus minus, there is a V of 0 divided by S. In this circuit, everything else is the same. V of S, I of S, and here this is a 1 divided by SC. Here we are representing the initial voltage in parallel, C times V of 0. So this is the very basic thing you have to remember. How can we represent the resistor, inductor, and capacitor in S domain? So I just repeat one more time. This is the resistor. So V of t is equal to R times I of t. So this is the voltage across the resistor. current across the resistor, and this is the resistance value. So in the S domain, we can represent V of S is equal to R times capital I of S. It's almost the same. In inductor, so V of T is equal to L times D divided by dt of I of T. That is the voltage applying to this inductor and then the current flowing through the inductor. This is the inductance value. And if you convert into this S domain, inductor is always with respect to the current flow. So this is I of S is equal to 1 divided by S times L times V of S. This is the how we are representing the current across the inductor in S domain. This is the initial current across the inductor. In capacitor, I of T is equal to C times D divided by dt V of T. So this is the initial current, and this is the initial this is the current flowing through the capacitor, and this is the voltage across the capacitor, and this is the capacitance value. So if you convert into S domain, so remember in the capacitor we are talking in terms of voltage. So V of S is equal to 1 divided by SC times I of S. This is the voltage across the capacitor. And if you consider the initial voltage, then that will be V of 0 minus divided by S. If we assume the initial voltage across the capacitor is 0, then we can ignore this term. So this is how we represent this. The advantage of the Laplace transform is that it includes both steady state and initial conditions. Steady state. This allows for obtaining both the steady state response as well as the transient response. So Laplace transform is helping us to get both or to achieve both steady state and transient responses. And the S domain equivalent elements can be readily used in first and second order circuits. So that is why we studied about how to represent the inductor and capacitor and resistor in S domain. And what is the equivalent equation. So I think when we see the problem, we will understand